So first of all, I wanted to point out how origami structures work. Normally, and especially with Kangaroo 2, uh, I told you that today we are going also to introduce some workflow with Kangaroo 099, because Kangaroo 099 has a different approach to origami than Kangaroo 2. With Kangaroo 2, it's like if Kangaroo 2 has been somehow simplified for the mass, okay? Because as it has become very popular, probably there was this kind of simplification in its behavior. Um, but we will see that Kangaroo 099 allows to do um, complex things more easily if you know how to handle it, okay? But anyway, in general, this is the origami problem in Kangaroo 2. You have a mesh. Basically, the mesh is made up of two triangles. And in this triangle, you recognize the diagonal, which is the folding line, and the tips that are the vertices that are allowed to move in space and to rotate around the diagonal here, which is the folding line. So once you create this scheme in your mesh, then you are able to use this component here, which is called the hinge. Um, the hinge is actually allowing your mesh to deform around the folding line. And he wants to know what is the fold start, which is basically this vertex here. The fold end is the other vertex. And then tip 1 and tip 2 are the two free vertices that can rotate around the folding line. Okay. And this is basically the fold angle component, which is an utility that you have in mesh here. If you already have a deformed mesh, this component here is capable of calculating the folding angle given the fold start, fold end, tip 1, tip 2. So we are not going to work with this because we are always starting with flat meshes. So we want the mesh to fold around the fold edges using the rest angle. So the rest angle is basically the angle that will determine how the origami will close, will contract or expand, basically. Okay, and as always, you have the strength. In this case, for example, calculating a strength is more complex because in this case, this action is something that is not bound to gravity or any other force. Okay, so normally if you have a complex simulation where you are using gravity and any other real life forces, you must only calibrate the strength of the origami accordingly. Okay, there is no let's say preset strength that you can use given a specific material. Okay, this component here, the only thing that it does is basically animate the origami. Okay, so of course, if you have, for example, an origami structure which is subject to gravity, and you want to, I don't know, like a roof, for example, and the gravity is basically making the origami structure fall, which means that the origami is unfolding itself, and you want to contract it once again, you have to apply a stronger force in order to balance the action of gravity. Okay, but there is no preset predetermined value for the strength of the origami. It depends on the situation you are simulating. Okay. Another thing that I wanted to point out is this website here. This website contains, let me open it for you. So it contains this origami simulator, which is quite interesting, not only because of the simulation of the origami, of course. This is interesting because you have access to the pattern that determines this kind of folding. So if you switch from simulation to pattern, this is the pattern of this particular origami shape that we were considering. And you can change the origami pattern here in examples. Like, for example, this is a type of origami that belongs to the tessellations category, which is the more interesting and also complex. And by the way, it is the water bombs. It's called like this. But you can change, for example, the pattern. And you see how the pattern updates. And you can switch to simulation once again and see what's the behavior of this particular pattern. And you can decide whether you are considering the flat version or the completely folded version. Okay, so you see how this particular pattern will work once you are basically folding it completely. There are also some advanced options, but we won't discuss this in detail. I strongly invite you to visit the website. It will be in the definition in the Grasshopper script, as you saw, and eventually use it for grabbing this information here. Okay. Now, this information, what we are going to do, for example, in our script, you can download this pattern here, like download it like a SVG, which is a vector file format. So you can open this file, for example, in Illustrator, and you can save it as an Illustrator file. And you will have, in that case, for example, you will have the lines with their respective colors, like red and blue, and also the black border of your area. Okay. So why this is useful? Because once you have it saved as an AI file type, you can directly import it into Rhino, and you will have access to the lines. And red lines and blue line means basically creases and valleys. Okay, so you have a direct scheme of the complex origami that you might want to create. So, for example, these are two patterns downloaded from that website. And I already imported this file here, this image here. This is called the Miura origami pattern. It's a famous pattern. It allows to fold a rectangular surface almost completely into a very small part, a very small piece. We will use this today, but not in the traditional way. We will use it to create some strange behavior, because I want to point out more than the standard behavior, or besides the standard behavior of this origami pattern, I want to point out also the problems that you can have when you try to work with this origami pattern, and also what are the possibilities that you have if you work in a non-traditional workflow, origami workflow. Okay, so it's going to be a comprehensive analysis, the one that we are going to conduct today. And so you see that, for example, here I imported, of course, at first I imported the origami pattern in Rhino, and then I let's say referenced the origami geometry here in Grasshopper. So you see that there are three sets of lines. The black lines are the border of the pattern. The red lines are, well, you can use them as creases or valleys. It doesn't matter, because this pattern is completely anti-symmetrical. So you would see that the blue lines are basically the same as the red line. And there are the blue lines, which is, of course, the opposite set from the crease or valley that you might want to consider. So you see that this was imported directly from the Illustrator file. Okay, so there is no need to waste time creating the meshes or the lines or creases and valleys and so on, because you can also access directly origami patterns online, like in the website that I showed you.
Carlo, the image that you have in the yes, that is a JPEG. It's just to reference. It's nothing to. I mean, you connect the Illustrator inside Rhino, and there is no connection with the picture that we have in the camera.
No, the image here is the image frame. Image frames use only raster image, so there is no vector here.
Exactly. It's just to remember what is the definition about.
Exactly. What are these curves about? Yeah. Okay. So let's start from a very simple scenario, okay, which is this one. This is, well, of course, this is very stupid, but it's very important to understand how you create a simulation in this case. In fact, what I will do right now is create it from scratch in order for you to understand what are the mandatory steps in an origami definition. Okay, so I'm going to grab a set of points. Remember that when you, for example, what I want to do now, I want to create a let's say quad mesh Okay, so at first I will select a bunch of points, a set of 4 points. And remember that if you want the mesh to be correctly oriented in space, you must select these 4 points counterclockwise, like this, for example. Okay, so you must double check that in your definition, your points are basically like sorted like this, counterclockwise. Okay, so once we have them, we can construct the mesh and say to this construct mesh that we want to use this set of 4 points. The construct mesh component, what it does, it takes a bunch of vertices and connect them or creates a polygon starting from these vertices according to the phase scheme. So phases is basically the connection scheme of the vertices that you pass to this input. And phases here is saying Q, which means quad, and this quad is obtained by connecting in order vertex 0 with 1, with 2, with 3. So basically this vertex, and then this one, and then this one, and then this one, counterclockwise. Okay, so we have a proper orientation with the positive normals facing up for this mesh. Now, the scheme that we saw here at the beginning is what we have to recreate in order to work with the hinge component in Kangaroo. Okay, so we need the diagonal here. Now, we are working with a single quad mesh. Okay, so it's no problem to use the triangulate component. The triangulate component, what it does, splits all the quads of a mesh into 2 triangles. Okay, that's it. We leave the mesh with 4 vertices and 1 single face, as you can see. And now we are getting a mesh with 4 vertices and 2 faces, 2 triangular faces. Okay. Then we need to start creating the Kangaroo behavior, Kangaroo simulation. Okay. So Kangaroo simulation, first of all, in an origami structure, all the edges must maintain their original length. Okay, so there is no elasticity playing any role in this kind of simulation. Okay, so it's quite a rigid body. Okay, we could define this as a rigid body where all the edges basically are rigid edges. So what I'm going to do, I'm going to take, for example, the well, in this case, we already have a mesh, triangulated mesh. So we can also do this in several ways. We can take the edge length component that takes the mesh. Length factor is by default set to 1. Strength is set to 1, which is quite weak, actually. We can eventually increase this value during the simulation if you see that this thing is going to deform too much. And this is enough because actually the edge length is not acting on the mesh. It's acting on mesh edges. So if you see, you have a mesh coming in the mesh input, but as output, what you get is basically 1, 2, 3, 4, 5 springs, which are exactly all the edges of the mesh. Now, the only problem in this case is that if you want to differentiate the behavior, for example, of this elastic mesh, let's call it elastic, by edge, then you cannot use edge lengths because this will apply the same length factor with the same strength to all the mesh, to all the edges of your mesh. So if you want to differentiate this, the behavior of these edges, then you cannot work with edge lengths. You eventually have to use a mesh edge component. And in this case, for example, you have access to the naked edges and interior edges, and you can apply an elastic force using, for example, length line. So if you want to differentiate it, you can also apply, for example, 2 length line and use 1 for the naked edges, 1 for the interior edges, or you can use any other rule for subdividing all the edges, for example, in different sets and associate a different elastic property to each of those sets, okay? But anyway, in our case, what we need is just a rigid set of edges. So I would say that length factor is correctly set to 1, but strength, I should increase it, for example, using a 101 in order to have an extremely rigid behavior for all the edges. So basically what we are saying is that these 2 triangles are not able to deform during the simulation, okay? We can also work in different ways because, for example, we already know from the rigid bodies a session that we had in the first day that we could also treat, for example, these two sets of vertices like point 0, 1, and 2, and point 0, 2, and 3 could be two separate rigid points set. Okay, so in this case, we will be saying that this triangle behaves like a rigid body, and this other triangle behaves like a rigid body. So when you want to create a simulation in Kangaroo, there is always more than one single approach to the problem. Okay, so it's up to you. If you feel more comfortable determining some properties in a way or another way, it's up to you. Okay, the important thing is that you basically don't make mistakes, okay, during the definition, or you don't create basically forces that are producing effects that are not, let's say, working in the same direction. Okay, so in that case, you might have some kind of instability during the simulation, or the simulation might crash, for example, or at least you will notice some strange behavior in your system. Okay, but anyway, in this case, it's enough to work with edge lengths. Now, what I want to do, what I need to do is to determine the folding of this body here. So the diagonal would be the folding line, and these two vertices would be the tips. So I go and take the gold mesh and the hinge component, which is this one, and it asks for fold start, fold end, tip one, tip two. These are all points. Okay, so if you see the black icon here, the black hexagonal icon is the icon for points. So the points, we already have them here. So I'm going to dispatch them because it's the quickest way when we have vertices. It's the quickest way because we can also do it like this. I can take a point container and see what is in list A. List A contain points 0 and 2, and list B, of course, contain 1 and 3. So 0 and 2, these points here, will be the fold start and fold end. And then there will be list B. Those points would be tip 1, tip 2. Okay, so I'm going to further dispatch the 2 points, point 0 and point 2, are actually in list A, list B of the second dispatch. And also I need tip 1, tip 2, which will be these 2 points here. And I'm ready because these are the fold start, fold end, and these are tip 1, tip 2. Now, we will see later on that there are also other commands that you can use in order to determine which are the fold start, fold end, tip 1, tip 2. But this is going to be the complex part. So when you work with origami structure, the more complex part is defining correctly the shape or the geometry of the origami structure. Okay, we will discuss it later on with complex meshes, so that you will notice how this thing works. Then the rest angle. Rest angle. Remember that in Grasshopper, angles are always measured in radians. Okay, and nobody wants to work with radians. Nobody healthy wants to work with radians. So I would use a radians component to convert the angle defined in degrees into radians. And I would say here, for example, an angle between 0 and 90 degrees. Okay, so this is the 90 degrees is going to be the maximum folding that we want for these two triangles. So I expect these two triangles to rotate around the folding line and take a configuration with an angle of maximum 90 degree. Okay, so this is what I am expecting. So we have the, let's call it the elastic mesh, and we also have defined the folding rule with the hinge component. Uh, let's see what happens, because actually we don't need gravity, okay? In order to simulate origami structure, we don't need gravity. We don't need a floor, because we only want to simulate the opening and close, the folding and unfolding of the origami structure, okay? So there is nothing more, we need nothing more than a rigid body definition, basically, even if with an elastic force like this one, and the folding rule like the hinge in this case. So what I'm going to do, I'm going to grab the solver, and I'm going to place the usual toggle and the usual button, and plug the goals. So the elastic net, which is this one, and also the hinge. Yeah, in this case, for example, I will not use the entwine method because I am not interested in performing further operations on the output, okay? But we already know that. So let's run the simulation. You see that it says converge because the mesh is quite rigid, okay? So there is no deformation occurring on the elastic edges. And the rest angle is set to 0. But if I increase this value, you see that these objects start to bend. And 90, you see that this angle here is exactly 90 degrees. Okay, so the rest angle is actually determining the folding and unfolding of the mesh. See? Now, due to the absence of gravity and other control forces, you see that if I start to play around with this one, as there is no constraint, basically this mesh starts to reorient in space, but it's non-relevant. Okay. Of course, you can anchor some points of this mesh if you want, in order to avoid this kind of floating object here, but it's absolutely non-relevant in terms of our simulation here. Okay, so this is how the origami principle translates into a kangaroo simulation. Okay, very simple kangaroo simulation in this case. Of course, we are going to work with more complex ones. So this is what you have. This is what you have here. Let me.
Giancarlo, in that definition, we don't have any kind of force applied, right?
No force applied. The only force that we are applying is the folding force.
Okay.
Okay. Yeah, this is the same thing, exactly the same thing. I only took a little more time to use the entwine method, and also I am showing the original mesh during the simulation. That's why you see the reddish surfaces here. And I worked with the mesh edge and the length line component also. Okay, but it's absolutely identical to the one that we just created. Okay, so I would simply get rid of this because we already have it, and just to confirm, this is what happens here. So we have this kind of rigid folding, like this, 90 degree. Okay, so everything. I hope everything is clear until now. It's very simple. Now we are going to analyze, well, I wouldn't say a more complex scenario, but yes, somehow it's totally different with respect to the previous scenario, because this starts to be, well, it might be stupid, it might sound stupid, but this is a more complex mesh. Okay, so this is the final result that we want to achieve. I'm going to show you what happens here when I use this angle. This is what happens. Okay, and this is something that we don't want actually to happen. We will see in a while what's happening in the simulation. Okay, so I'm going to switch off the simulation, hide the preview of Kangaroo, and I'm going back to the beginning. So the beginning is this. Now, this is a mesh that I created in Rhino, okay, and not in Grasshopper because of one particular consideration. We saw that the construct mesh component that we might want to use in Grasshopper asks for vertices and then asks for faces, and faces is the connection scheme. So if you only have 4 vertices, it's very easy to understand what's the connection scheme, okay? It simply connects the vertices in the correct order, 0, 1, 2, and 3. Okay, so the only thing that you must take care of is determining the 4 points here in the correct position in space, like counterclockwise. Okay, but what happens if, for example, I try to create this mesh here in Grasshopper? Okay, so in that case, for example, I will be creating first point, second point, third point, and fourth point in this order. So it will be 0, 1, 2, and 3. But then I need this other quad here. And then I will have point number 4 and point number 5. And there I also need, for example, this quad here, where I will have point number 6 and point number 7. And I need also this one, which is simply point number 8. Now, let's stop here, okay? So in order to create the mesh in Grasshopper with a construct mesh component, the faces scheme should be, the first scheme should be Q 0, 1, 2, and 3, okay, of course, in order to create this quad here. But when it comes to the other quads, this will be Q 1, 4, 5, 2. And this other one would be Q, for example, 5, 6, 7, 2. And this can be Q 3, 2, 7, 8 in order to create this one. Now, how can I extrapolate the indices of the vertices that I want to connect in order to create this simple mesh with 4 quads? It becomes a very boring and long process, okay? So we don't create this kind of controlled meshes in Grasshopper. It's better to create them in Rhino, okay? So in order for you to never try to do this at home, I will leave this scheme here and will give a red color so you know that you never want to create a controlled mesh in Grasshopper unless you have plenty of time and plenty of patience, okay?
Not even if we have one mesh and we divide it afterwards.
This is another thing, okay? So if you create a complex mesh by subdividing an existing mesh, this is another thing, okay? But I'm talking about the original mesh, the first mesh that you want to work with. You never create this kind of controlled mesh. Controlled mesh means a mesh controlled by vertices, okay? And you don't want to do this in Grasshopper. So in Rhino, it's way more easy because you simply go into mesh, polygon mesh primitives, 3D face, and start clicking counterclockwise 4 quads. Remember that Rhino 6 allows create n-agons, which are meshes with more than 4 sides. But I do not recommend that you work with n-agons. Just work with triangles or quads, okay? So when you hit the 4th vertex, just enter, and you have the first quad. Then you need the other quad. You simply switch the vertex snap on, and then you can snap to this vertex, and then second, third, and fourth point. And then first, second, third, and fourth. First, second, third, fourth point. And you can create as many quads as you please in this case, okay, like this. Of course, these are 6 separated meshes, okay, but you can select them and join them all together. So you have one open mesh in this case. And this is the mesh that I imported here in Grasshopper, okay? So I created it in Rhino and imported in Grasshopper. If you want to work with a controlled mesh, this is the best workflow that you can create. What happens with this mesh? Now I want to reproduce the same scheme that we have here, okay? And you see that in the previous example, we have used the triangulate component, okay? But this is not good for our workflow when we work with more complex meshes. If you have one single quad, there is only one way that you can triangulate that mesh. Well, actually, there are 2 ways, but any of the 2 ways, it's good for us because we don't care about the orientation of the diagonal. But what happens if I apply the triangulate to a complex mesh like this? Let's take a look at this. You will see that diagonals are coming out in 2 different orientations, more or less randomly, okay? So there is no way to control this using the triangulate component because you see basically there is no options. If you right click on it, there is no other parameter. There is nothing you can do. You can simply rely on the result that the triangulate component provides. So that's why I am creating this red group and a X on it because I don't want you to use this, okay? But we need these diagonals. So we must create the diagonals, okay? How do we create the diagonals? Well, there is this component which is called mesh explode. Control Alt click. You see that it belongs to standard mesh toolbar in the analysis group. Okay, so it's not a plugin. Why am I using this? Because this explodes a mesh into its faces. Okay, you might know that in Grasshopper, explode is usually, let's say, created by a different type of command, which is the deconstruct. Okay, so if you use deconstruct, you are basically exploding things. So in this case, for example, you might notice that there is a deconstruct mesh component. But if I use the deconstruct mesh component, which is this one, by the way, if I use it right directly from here, what I get is vertices, which are the points, but I need the faces. And as the construct mesh asks for a connection scheme, faces is actually giving us a connection scheme. So this is the connection scheme of my Rhino mesh. You see 0, 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. Okay, you have this kind of scheme. But I don't need this. I need the faces, the physical faces of the mesh. That's why I use this mesh explode component. Okay. Well, I will not go into analyzing this component because I don't think we have enough time today. But anyway, once we have the faces, each face is a separate mesh. 4 vertices, 1 polygon, 1 face. So we need to create, for example, the diagonals, okay? And we want all the diagonals to be oriented in the same direction. So what I do here is now, yes, I do apply the deconstruct mesh because I need the 4 vertices to create the connection line. Okay, so once I have the 4 vertices, I dispatch them one time, and in list A, I will have vertex number 0 and vertex number 2 for each of these faces. And I dispatch these 2 points, so they are in 2 separate sets, and I create these lines. Okay, so now we have the lines as diagonal, all oriented in the same direction. Okay. Then if I cannot use the triangulate component, I still need to split each quad into 2 triangles because I want these 2 triangles, 2 virtual triangles here to fold around the diagonal line that we just created, okay? But I cannot use the triangulate, so I need to split this mesh here, this mesh quad, into 2 triangles. And in order to do this, I converted the original mesh into a polysurface. This component here, Control-Alt-Click, belongs to the pufferfish plugin. Okay, so it's not a standard grasshopper component. But in any case, this is just to make the process more easy and more compact. But you can still do this in Grasshopper as well, because in standard Grasshopper as well, because once you have your 4 corners for your from your mesh explode and then the deconstruct mesh, you can also do something like this. You can take a list item and separate these 4 vertices into 4 separate channels like this. And then you can create a 4-point surface like this. So here we have, instead of converting the mesh into a polysurface and then exploding the polysurface in order to have access to its surfaces, in this case, I am doing exactly the same, but with standard Grasshopper components. Okay, so we have here 6 surfaces originated by the 4 corners. Okay, I'm going to flatten this if you want, and I'm using the surface split command in order to split each of these faces here with the respective diagonal. So if I substitute, for example, the faces coming from the mesh to polysurface and explosion here in surface with this one, I will get exactly the same result. Okay, so I am splitting with these diagonal lines our quadrangular surfaces. Okay, and then we have access to these fragments, and these fragments are basically 12 triangles into 6 branches. So I want to join all these surfaces together in order to have this polysurface here, which is made up of triangular faces. And I'm using a nice component here, which is called Simple Mesh. This is standard Grasshopper, by the way. So Simple Mesh is here in the Mesh toolbar. In the utility group, you have this Simple Mesh component. Okay, And this actually converts each of the faces of the surfaces of a B-rep into the simplest mesh possible, okay? And therefore, we are back to our initial mesh, which is basically now has been triangulated using the correct diagonal orientations. Now, I did some operation here. This is actually not strictly important because we only need to work with the edges and with folding around an edge. But it's important to have the mesh oriented properly. Okay, you see that, for example, if you take a look at this one, it appears like matte, dark matte object. Okay, while if I simply join it and weld it, you see that it becomes bright red. Okay, so this means that this mesh had some problem. Every time you see a mesh representation like darkish, then there is something that you might want to adjust for that mesh. Okay, so I simply tried with a join meshes and weld. So I welded perfectly the mesh, and this is actually what happens because weld is set to true actually. And then just to be sure, I'm using a mesh unify normals. Oh, by the way, this is Weaverbird's plugin. Okay, this is not standard Grasshopper component. If you want, you can use also the mesh join, which is absolutely the same. And then once you have mesh, a join mesh, you can use the weld mesh component, which is doing basically the same. And then I am using the mesh unifying normals, which is another utility from standard Grasshopper mesh toolbar, which is actually unifying the normal direction for our mesh. And you see that we get exactly the same result because the mesh join and weld mesh are doing exactly what the Weaverbird's component does, join meshes and weld. Okay, so let's keep it simple. I do recommend only that you have Weaverbirds available. And this is the mesh that we are going to work with. Okay, so finally we got to the correct representation of our mesh. Now, this is something that this process here, it was quite easy. Let me go back to the original definition. This process here, which is quite long and boring, this is mandatory. I mean, when you work with origami, you must prepare the mesh in order to deform in the correct way according to the desired effect. Okay, if you don't do this work, your origami simulation will simply produce some kind of weird result, as we will see later on. Okay, once we have the mesh, and we also have the points here. Okay, all the points of each face are contained in this vertices output. These vertices here is being sent to a list item in order to separate the 4 points belonging to each panel into 4 streams. Okay, and this is because we need to feed the hinge component with fold, start, fold, and tip 1 and tip 2. Okay, now if we take a look at the mesh as it is, and we take a look, for example, at this output from the list item, we recognize that the first output is the lower left corner. Okay, you see, because in this polygon here, we miss this vertex, this one, and this one. So we only see the lower left corner. Then there is the +1, which is the lower right. Then there is +2, which is the upper right. You see here, we miss the upper left, and this is the upper left. So fold start, fold end are the extremes of the diagonal, which is I and +2, because I is this one, and this is +1, this is +2. So I and +2 are fold start, fold end, and tip 1, tip 2 are the remaining vertices, +1 and +3. Okay, so you have to pay attention to which points you are connecting to the fold start, fold end, tip 1, tip 2. And then there is this other component here that I used in this definition, but this is something that normally shouldn't be necessary in your definition, because what it does is simply avoid one triangle or one surface of your origami to fold through the opposite surface. Okay, so it's like a constraint, basically. But normally, if you set the angles properly, you shouldn't run into problems with this folding behavior here. And this is the rest angle. okay? And of course, we also need this mesh to be, let's say, elastic, but with a length factor of 1, okay? So there is no deformation of the edges. If you don't do this, as soon as you start decreasing the rest angle, this object will still bend and fold along these diagonal lines, but each time it folds and unfolds, the springs, the edges, will tend to expand a little and a little. So little by little, this thing is going to become wider and larger and so on. So we don't want this. That's why we must provide this kind of control here. And let's turn off this one. Let's turn on Kangaroo, and let's run the simulation. And now, if everything is properly set, we should see this thing here folding along the diagonals. Now, what's the problem in this case? The problem in this case is that we are using the same angle for all these diagonals here. Okay, so this is an origami structure, but it's folding in an incorrect way. Why? Because eventually, if we have the first diagonal here is folding, it's basically the two triangles are folding upward. Along the second diagonal, the triangles should fold downward. Okay, so we must invert the folding angle for each diagonal. So this is, for example, a positive angle. This will be a negative angle all along this diagonal here. This will be a positive angle once again, and this will be a negative angle once again. Okay, so we will do this in a more complex simulation later on. But you see that not only we must provide a rest angle, we must adjust the rest angle according to the creases or valleys that we want to consider in our origami simulation. Okay, and this is the only thing that I'm going to do here is, for example, change this slider from 0, 120 to minus 120 to 120. So for example, now we can see that if I go positive, I have this. If I go negative, I have the opposite. Okay, so you see that you can work also with negative rest angles. Okay, let's switch back to 0. Let's turn off this thing. Okay, is everything clear? Do you need to clarify something?
Carlo, I have a doubt.
Yeah.
What's actually no fold through command is actually doing in that? How is it actually working in this situation? Can you elaborate that?
In this particular situation, nothing.
Yeah.
Nothing,
Okay.
because I am not, let's say, I am not setting this angle in a problematic way. Okay. What this thing should do is that, for example, if you have a situation like this one, okay, where this tip rotates around this edge, this tip rotates around this edge. If this angle, for example, becomes quite extreme, the two triangles start to be quite close to each other. So the no fold through avoids that this triangle, for example, passes on this side and this other passes on the other side. Okay, but in our case, this is doing nothing. But I told you that normally this is something that eventually you could never use this function here. If you set things properly, basically you don't need this control. It depends all on the rest angle. But in very complex simulation, in very complex origamis, for example, origamis that you can download from this website are quite complex, then in that case you might want to implement this kind of strategy. But it's very simple, because once you detect what are the fold, start fold, and tip 1, tip 2, you use them exactly the same way as for the hinge. You use them for the no fold through component. It's absolutely identical. But in our case, it's doing nothing. Absolutely.
Okay, if this component is actually deselecting the connection which we are connecting to this Kangaroo main component, even it works.
Actually, it works only if it is required to work. I mean, let's do a quick example. Okay, so I'm going to hide this kangaroo for a while, and I'm going to work for a moment with this mesh here. Okay, and what I want to do with this mesh is simply contract the mesh. Let me grab the edge length component. Contracting the mesh means that I want this to tend to zero length factor. Okay, and the only thing that I want to do is this one. Okay, so I'm going to grab a Kangaroo component here, and I want it to work only with this. So if I set this to 0 and run this mesh will collapse into a point. Okay, but if I, for example, do this, deconstruct mesh, and grab all the vertices and apply, for example, a sphere collide to all these vertices here with a radius. Okay, so in this case, for example, I will set the radius to 500. Okay, like this. Now, the sphere collide, what it's doing is actually simulating a sphere with a radius of 5 around each of the mesh vertices. Okay, and so as soon as one vertex get close to the other vertex, at a distance of 5 plus 5, they cannot get closer than that. Okay, so if I run the simulation, this mesh collapses, but it cannot collapse totally because there is this sphere collide that avoid this point to get too close to each other. Okay. Of course, if, for example, if I don't set this to 0, for example, I set this to 1. In this moment, this sphere collide is present, but is doing nothing because the mesh is not collapsing enough to make the sphere collide work, but it's here. So as soon as these start to contract, it reaches to a point where the sphere collide starts to avoid the mesh from collapsing, which is this point here. Okay, but you can also, for example, work with this. If I increase it, you see that the mesh is expanding once again. If I decrease this, the mesh can contract more and more and more. Okay, so not all the forces, not all the goals work just because they are connected to the bouncy solver or to any solver that you might want to use. They work only when the system has reached to a configuration that demands them to work. Okay, and this is the case for our no fall through. Okay, so in this case, for example, it is connected to the main solver, but it's not working because it is not required to work. Any other doubt?
Okay. Yeah, that's clear. And one more doubt is we started with a multiple mesh quadrilateral faces. So
Yes.
what if we want to start with a surface and crack the geometry? So in this case, it's a simple geometry, so we can visualize it.
Yeah.
So if you actually shown some of the complex geometries from the website. So how is that being done actually?
We will see it later. Actually, what I'm going to teach you today is that not everything that you want to do must be done in Kangaroo 2. Okay, there are some things that are easier to achieve in Kangaroo 099, but we will discuss this in a while. Okay. Okay, so let's start with the interesting stuff. Okay, so for example, this one. Now, this thing here is actually based on the pattern that I was showing here on top. It's based on this pattern here, the Miura origami. Okay, so basically what we need here is to recreate this situation, this configuration. Okay, now I have these edges. Okay, these are the 4 edges of our pattern. Okay, I'm going to copy it here, and these are 4. I only need, for example, this one and this one. So I'm going to recreate a mesh starting from this pattern. Okay, so I take these 4 lines. This is because I got rid of the original pattern imported from the Illustrator file. Okay, so you might want to use exactly the pattern from the Illustrator file in order to import it into Grasshopper. But anyway, I internalized all the lines in Grasshopper, so I have it available here. And if I, for example, list item this, you see that, let me turn off this one. You see that the first line is the lower border, the lower edge. I don't want it. And then there is this one, and this one. So it's +1, +3.
Carlo, a really simple question.
Yeah.
Because never import an Illustrator file into Rhino. It's just the AI file extend you import, or you just export as a DVG from Illustrator?
No, AI.
All right.
So for example, here are the AI. This is the Miura Origami. This is our folder for the course. If you want, I can show you. Let me copy this path, and I can file, import, and go. Oh, we're already in the right folder. So this is the Miura Origami in AI format, and you open it. You just decide if you want to scale it or not. I scaled it because if you use Illustrator points and convert it into Rhino unit, in this case, it will become very, very large. But 10 points converted into 1 unit, and okay, and here it is. This is the pattern from the website in SVG. Perfect. Converted into Illustrator. And you see that it maintains the colors, so it's very easy. You can select this line, select by colors, and you are selecting all the valleys or creases that in your pattern, okay? And you can import them in Grasshopper. But anyway, I am quite sure that we are going to run into a problem right here, because let me double check. Oh, okay. No, I have the correct pattern. Correct pattern because you see this is a seamless pattern. Okay, so it doesn't matter what extension you give to these repetitions. Okay, so I decided to eliminate the last row of cells basically in order to have a more easily manipulation inside the Grasshopper definition. Okay. But I didn't even want to point it out, but anyway, you can simply change your algorithm according to the number of repetitions that you want to consider for this pattern. But anyway, we decided that we want to work with line +1 and line +3. So if I plug...
Why is it easier if you remove one line?
Because if I remove one line, I can work with even repetitions. Okay. That's the only reason why. So basically, this is what I did here was take the left edge and the right edge, create a loft surface. Let me turn off the preview, which was this one. Okay, I have two different workflows because I want to show you exactly what happens if you don't define things properly. Okay, so basically, I have these two opposite edges. I create the loft surface, which is a flowing between simply one edge to the opposite edge. I need to subdivide this into the quads that we saw in the original pattern. So I exploded this polysurface. Remember that if you have discontinuities in the edges, in the cross sections, you get a polysurface as a result. You see open B-rep. And I explode the B-rep, obtain each of these stripes here as separate surface, and divide each of these stripes into 12 panels. So we have here 2, 4, 6, 8, 10, 12, 12 by 12 panels, okay? Which is basically 144 surfaces. And I convert them into mesh panels. So 144 quads. We saw this is the mesh surface component, but we also saw that we can use, for example, the simple mesh component and start directly from the B-rep object. So if I join all these surfaces into one single B-rep and then use this one, I get exactly the same result. But I also need these meshes to stay divided, like in this case, these are 144 meshes, individual meshes, okay? I didn't join them yet. So why? Because I need to define, for example, in this case, the same scheme, which is the diagonals. So I wanted to create, use the Miura pattern, not in the usual way, Okay, you can find plenty of tutorial, and eventually you will see. I will give you a method for using exactly the pattern that comes from, for example, the website, in order to create exactly the Miura behavior. The Miura behavior is this one, by the way. Okay, is this one. We are not going to create this folding for the Miura origami. We are going to create a different one working with the lines. That's because I want to point out that the preparation of your mesh is fundamental in order to simulate the behavior that you want. Okay, so we will discuss this later when we introduce 099, Kangaroo 099. But anyway, we have all the meshes here, 144. I deconstruct them in order to have access to the four corners of each panel. So this is a data tree with 144 branches, each containing 4 vertices. And I dispatch first, dispatch second. So I have exactly the opposite corners. And then I create the diagonal lines. Okay, so this is what we just did in the simple scenario. Okay, so we have the original meshes, and we have created the diagonals all oriented in the right direction. Now, in order to double check, yeah.
The relay component, what is the function of it? I never understood it.
I use it only for organizing the definition better. There is no use, but it's like a, I could call it a switch along a cable, a wire. So for example, this thing, you can control this relay if you want. So basically enable, disable. It's the only thing that you can do. So if you want to work with two different workflow, you can use a relay in order to turn on or off a particular workflow and work with the other one eventually. It's like a switch.
Okay.
What I wanted to point out is that if I try to triangulate this, you see that I have diagonals in both directions. Okay, it depends on the strap that we are dividing. This is not predictable. Okay, so don't use triangulate if you want to work with a controlled origami structure. Now we have the mesh, and we have the diagonals. Okay, I use surface split because this is a mesh conversion starting from the panels, which are NURBS surfaces. I use surface split in order to create the triangles, starting from the line. So these are triangular surfaces, 288. And then I deconstruct these surfaces, these triangular surfaces, have access to their 3 vertices, separate the 3 vertices into 3 separate channels, and send them to a construct mesh. Now, this is not evident because I did it in an implicit way, but I am connecting here 3 vertices per branch. So if we take a look at, let me get rid of this group for a moment. If we take a look at how this data is organized inside this data tree, let's do it like this. So I connected first, second, and third. Okay, so this construct mesh is receiving 3 vertices at a time, 0, 1, and 2. Okay, these are the 3 corners of each panel. So I need to give the faces the right connection scheme if I want to create the triangular panels, the triangular polygons. Okay, and so in this case I did it the hidden way. Here I just set mesh face. The original was Q 0, 1, 2, 3, and I turned it into T, which means triangle, simply connecting 0, 1, and 2, which are the 3 vertices we have inside each branch. Okay, so you can provide this scheme as you want. Okay, but I preferred to do this inside the component input, because this is something that I don't want to edit, never. Okay, so I prefer to keep it here, and difficult also to edit because this must be like this. Okay, and then there is the let's say the interesting part. Okay, because it's true that we have all triangles here, but we want these triangles to fold along this diagonal. And so when we use the hinge component, the hinge component must know that this is a fold start, this is a fold end, and these are the two tips. And this for all the triangles in our mesh. So in this case, we don't need to work with separate triangle. We must join pairs of triangles to create this mesh with 4 vertices and 2 triangles inside. So we must go back to our initial scheme like this. And in order to do this, what I did was dispatching the triangles. So if you take a look at the result of this, I'm going to use a mesh container and see what happens here. This is the mesh triangle coming out from A. Okay, so it's this one. And in B, we have this one. So if I join A with B, like with this mesh join, I get the same geometrical aspect of the original mesh, but our mesh is actually is not, let me, okay, you see that here we have 288 branches, each one containing 1 triangle, okay? While here we have 144 meshes, each one made up of 2 triangular faces, as you can see. So this is the mesh that we want to use for our origami simulation, okay? So each time you work with origami, you must understand how to create the proper mesh aspect or topology, which is the proper term, in order to create the right origami simulation, okay? And so once we have prepared this, which was the real problem in this definition, we can start to implement the Kangaroo goals. Okay. So, for example, I took all the. This is the incorrect thing that I wanted to point out. Okay. So what I'm doing here, I am giving elastic properties to these objects here. Okay. So this is the mesh made up of pure quads. It has no diagonal lines. Okay. So I take this mesh and join all the meshes together in order to have one single mesh with 144 faces, while the triangular mesh has 288 faces total. So I'm taking the quad mesh and extracting all the edges and giving elastic property to those edges in order for them to remain like undeformed during the simulation. Okay, very rigid, very stiff springs. And then I also applied here some gravity in order to start playing also with different different scenarios. Okay, so I took the mesh, the quad mesh, extracted all the vertices, and I am applying a load to this. The load is initially set to 0 because you see that the floor is disconnected. So I don't want this mesh to fall. So either I leave the load to 0, or I plug the floor to the solver. Okay. But in any case, I will work with load 0 for now, and then we will switch things with these 2 components here. So this is all. That's it for the mesh, okay? And then I take the real mesh or the good mesh and use it for implementing the hinge or the origami structure. So this is interesting because here, remember that we were taking all the vertices and then analyzing which was the fold start vertex, the fold end vertex, and so on. Okay, but there is also a command in Kangaroo which is called the hinge points. It's a mesh command. You see, it's here, hinge points, and this gives you the 4 points of a mesh which is ready for the origami simulation. So it must be a mesh with 4 vertices and 2 triangles, 2 faces, and gives you the vertices 1, 2, 3, and 4. Now, the only problem with this is that you don't know exactly which is the fold start, fold end, tip 1 and tip 2. You have to analyze them, okay? So for example, if I have the mesh here and I take a point container and plug output number 1, in this case, I see that my vertex is this. And this is a fold point. If I take number 2, I get this. This is the other fold point, okay? And therefore, if I take 3, I get this, which is a tip, and 4, it is a tip. So if you want to work with these hinge points, you must double check who is each of these output in terms of false start, false end, and tip 1, tip 2, in order to connect them properly in your hinge components. Okay, so let me go back to here. And here are the points connected already into false start, false end, tip 1, tip 2, and also in the no fault through in case it is necessary. You see they have separate strengths. I do recommend that you always consider the constraints more important than the goals, than the actions, because if you have a constraint, you want that constraint to be effective for your simulation. So the strength should be higher. It's like, I repeat, it's like working with an anchor point. Anchor point is stronger than any other goal, okay? Because either it's present or it's not present. If it is present, we want it to work. And we don't want it to be moved during the simulation. The same for the no fall through, for example. It's a constraint. So I want it to have more strength than, for example, the origami folding. Now, what happens in this case? I am voluntarily creating a mistake here because I am applying elastic properties, and well, loads and floor are not relevant because this mesh here, the quad mesh and the triangle mesh, have the same vertices. Okay, the only difference they have is these diagonal edges inside each quad face. Okay, so I am using the quad mesh to give elastic property to these edges. So basically what I'm doing is not giving elastic properties to the diagonals. Okay, so this means that if I have this quad here with a diagonal edge that I am not taking into account for the elastic properties, what I'm saying is that this edge here, this edge, and this edge, if they have length 1, length 2, length 3, and length 4, this will be constant during the simulation. But this, no, it won't be. It won't remain constant during the simulation. So this means that this object can stretch, for example, in this direction. So these points can move basically like this and like this. Okay. So this is what's happening in our case. Okay. This is not correct, I repeat, but I wanted to point it out because what happens if you don't have the right origami geometry set up? Okay. So in this case, we have a incorrect setting for the elastic property, while the hinge and the origami simulation is set properly because we are working with the triangular mesh. Okay. So let's see what happens when we fire the simulation. We have the entwine method here. So I just turn on the explode tree. When I have the edges visible, you see that we miss the diagonal edge and the mesh, which is the light red surfaces, including the diagonal edge. So let's run this. We have this kind of behavior. And you see that this thing starts to bend in a weird way. Well, weird but nice way. Okay. So what we are doing here is basically simulating an origami where we have the panels inside these quads are made up or can be made up of elastic fabric or something which is not basically too stiff, too rigid. This allows, for example, these quads to compress along the opposite diagonal. And therefore, you see that here on this extreme corner, this quad is compressed along the opposite diagonal. Okay? And so the origami takes this nice shape because we are simulating something that is not completely rigid, especially in the this diagonal direction. And of course, this is not correct. So this is a nice result. Remember that when you browse the web, for example, and look for parametric or computational design example, 99% of the results that you see are either errors or something that you can simply not produce in real life. Okay, so you know, I'm quite cynical in this approach, but that's my idea of standard grasshopper or parametric design production. But anyway, I want this to work properly. Okay, so we miss one step, and I'm going to analyze it here. So I go back to the original shapes or the original geometries that we had here, and I repeat the process, but in the correct way. So let me go into the top viewport, and here we have our list of 144 quads, triangles. You see here we are taking the original mesh, 144 meshes, because remember that when we joined this, we were joining this triangle with this triangle. So it says 144 meshes, but each mesh is made up of 2 triangles, okay? And then what I'm doing here is preparing the origami, because what I want, if we take back the diagonal lines, what I want to simulate is that our mesh is going to fold along this line with a positive angle, along this line with a negative angle, positive angle, negative angle. So I want this origami structure to pack in this diagonal direction, the opposite diagonal direction. So this is a real origami effect, okay? So what I'm doing here, I'm taking the mesh made up of 4 vertices and 2 faces topology here, and sending one of these quad in one set and another one of this quad in another set. Well, I mean quad as the result of 2 triangles, okay? So we have basically these columns here of meshes, okay? That's why in this moment, it becomes clear why I eliminated the last stripe here from the original pattern, because once I have this, I am going to create the same set of meshes, but in a data tree structure. So in order to do this, what I'm doing here, I am basically subdividing these 72 meshes. Remember that this is just one single set, including 12 plus 12 plus 12, 12, 12, and 12. Okay, so I need to actually divide this by columns, okay, physically. So I need to create a partition list where each branch will contain just one of the columns, okay? And the amount of faces, the amount of meshes that I have inside each column depends on the amount of division that I performed in the paneling of the original loft stripes, okay? So basically I take this one, divide it by 2 here. We have a division by 2 in order to create chunks, each one containing 6 elements, 6 faces. Then I do a flip matrix because I don't want to work in columns. I want to work in lines. And so when I dispatch this, you will see that the first wire is giving me these panels here. Let's go back to our original mesh definition. Well, actually, this one. So this one is giving me considering this set of 4 meshes. This one is giving me the upper left mesh. This is the lower left mesh. This is the lower right mesh. And this is the upper right mesh. Once I have this, what I can do is take, for example, the lower left plus the upper right, and see that all these meshes here are basically defining these diagonals here, these alternated diagonals, okay? So I took them and brought them inside one single component, okay? And I did the same with this other thing here. So I am simply basically subdividing all these meshes here into 2 diagonal sets, because what I want to do is consider their diagonals. So this set of meshes will fold along this line and all these lines here with the same, let's say, positive rest angle, while this other set will use a negative rest angle, okay? So that's why I subdivided these meshes into these 2 subsets. Once I have these, I can use them to implement, well, actually I can use them to create the proper mesh. So I want to work with the proper mesh means that I don't want to apply the origami structure to a mesh that doesn't take into account the diagonals, okay? I want the diagonals to be part of the elastic behavior of this mesh. That's why I took these two subsets, joined them all together, okay, and use this in order to calculate all the mesh edges. You see that now the diagonals are included, and gave elastic properties with very high value of the strength in order to don't have any deformation also along the diagonal direction, okay? And I am also applying the load and the floor and so on. And then I use these two subsets to create two different hinge behaviors. The first one, you see that there is always this hinge point, hinge, and no fall through. They repeat twice, of course, because I have this rest angle. I want it to be negative for this hinge, and I want it to be positive, like simply connected here, for the second hinge. So the second hinge, which are these, are using a positive rest angle, and this one would be using a negative rest angle. Okay, so you see that the preparation is fundamental. Now, in this case, if we go here and visualize the result, let me go into perspective because I wanted to see it from the diagonal point of view, and run the simulation, and go here, take the rest angle, and start to increase it. So if we increase it, you see that now the behavior is exactly what we expected. Okay, this thing is starting to fold along the diagonals. Okay, and if I increase it, increase it, increase it, increase it, you see that this thing starts to bend, to fold properly. It is packing along the opposite diagonal. So basically, this is the correct behavior. You see that if you want this object to pack completely, you must reach 180 degree. I do not recommend you do this because in real life, in the real world, two objects cannot coexist in the same exact location in space. So it is a mathematical or a totally hypothetical behavior, the one that uses a rest angle of 180 degrees. Also because when you try to fabricate or produce this, you are not going to work with materials that have zero thickness. So you cannot simply pack this totally like with 180 degrees into one single flat surface. Okay, there will always be a thickness that you must take into account. So don't ever exaggerate with this angle. Just once that you have the right behavior happening, you know that if you increase this angle, you will get a more compact packing. Okay, but the important thing is to double check that the origami is behaving properly. Okay, so for example, in this particular configuration here, it depends, talking about fabrication or producing this kind of structure, it depends on how you want to produce it. Now, if we want to consider only these stripes here, and these stripes are rotating, are folding basically along these large diagonals, uh, it could also be useless to produce the single triangle. We could also produce directly all these stripes into one single piece. Okay, so this can be probably the best way of producing this kind of origami. Of course, you must take into account what's the size of your modules. So if you, for example, think about this large stripe of triangle here, probably it becomes very large, and I don't know if you have the possibility to produce it in one single cut, for example. But anyway, you can optimize production like selecting which triangles can be joined together in order to create the basic module of your origami structure. Okay, but in this case, you see that even if we are not working with the exact, let's say, Miura origami behavior, we can use the same structure, the same mesh in order to produce another type of origami. Everything depends on how you program the folding along the edges. Okay. Now, the reason why I'm not creating the Miura effect or the Miura origami with this definition here is because I should be working too much with Kangaroo 2 to obtain exactly this folding behavior. Okay, so this is something that it becomes very, very easy with Kangaroo 099. So the problem is that with the Miura behavior here, you see that the quad faces stay basically the same. Okay, so you are not working on triangles, you are working on quads. So in this case, for example, as Kangaroo 2 uses hinge programmed like this with folding along diagonals and tips, in this case, it becomes very difficult to organize your input geometry for the Kangaroo simulation in order to behave like the Miura pattern. Okay, while if you work with the Kangaroo 099, things become easier. That's why in the next section, we will be using this, which is Kangaroo 099, in order to simulate a different approach to origami structures. Okay, so in this case, I will add this to this group. So it becomes part of the group. And let me regroup these all together so you will have it available and well in order. Do you have any questions, guys?
I have a couple of questions.
Yeah, tell me.
The first one, just to confirm that I understood correctly, the second and last part of the definition is the correct one because of the behavior of the folding part that has a negative and a positive angle.
Not only that. In
Okay.
the first part, remember that I was considering elastic properties only for the quad edges and not for the diagonal. And so this makes the quad edge, the quad mesh, capable of expanding or contracting along the opposite diagonal.
Okay.
And we don't want that. We also want this diagonal to be stiff and rigid. Okay, in an origami structure. And that's why, for example, the problem is that you see that here, for example, the things that are being sent to the elastic property definition is this mesh here. There is no trace of the diagonal lines. So diagonals are not taken into account because simply they are not being calculated. Okay, so this mesh has no elastic constraint along the folding lines, while we are considering diagonals for the folding behavior, for the origami behavior. And so these quads here, due to the fact that there is no constraint along the diagonal, this quad can basically stretch because this diagonal is not rigid. Okay, there is no elastic property for the diagonal. And also here we had one single rest angle. They were all positive, and so this surface can only bend in one direction. Okay, while here what we did was considering basically the triangular mesh, which is this one. We were considering the triangular mesh, so we have also the diagonal lines, diagonal edges taken into account in the elastic property definition. So you see that this is the mesh that we are sending to the mesh edges. So we also have the diagonals taken into account. And we have differentiated the rest angle in between positive and negative rest angle for the two sets of diagonal direction. So it is two different actions that we took here in the second simulation.
All right. And the second one and last question is, I got a bit lost when you were speaking about inside the component, you make a differentiation between triangulation and quad, just giving a T instead than a Q, if I understood correctly.
Yes. It is like here.
Yes.
Okay. Look, I will make it very, very simple like this. Okay. So let's say that I take a point container. Okay, and then I set multiple points like 1, 2, 3, and 4. So potentially I can create a quad because I have 4 points. If I construct a mesh and plug these vertices, I get this quad because faces the connection scheme is set to Q, so it is set to create a quad, connecting vertices in this particular order, which is 0, 1, 2, and 3. Okay? But if I go, for example, here, set mesh face, and say, you know what, I am giving you 4 vertices, right? But I don't want to connect them all. I want to connect just 3 of them in order to create a triangular face. So what I want to connect is point 0 with 1 with 2. So I get rid of the last, commit changes, and I get this one. So this construct mesh is using 4 vertices, is receiving 4 vertices, but it is using just 3 of them according to the connection scheme, which says I want to create only a triangle with 0, 1, and 2. If here, for example, I go into faces and say, set multiple mesh faces, okay, and say this is the first one, and then I want a second one that connects 0 with 2 and 3. So this one with this one with this one. Then I will get here, well, it says input parameter faces failed to collect data. Why? Oh, I deleted everything. Sorry. Okay, let's start from scratch. So I would say here triangle, and then I want 0, 1, and 2. Okay, let's see if commit changes. No, it's not accepting it. Let me see. Oh, we might have discovered a bug, guys. We might have discovered a bug. You see that if I do this like in set mesh face, I get the proper result. If I do this in set multiple faces, everything disappears. Nice. Okay, so this is a bug. I didn't know it, sorry. Maybe if we manage mesh face collection, I don't know if this can work. You see, this is the first scheme, okay? And this is also interesting because you see that it always uses 4 corners, you see, but the third and the fourth are the same point index, okay? So what I'm going to do here, I'm going to add item, okay? And what I want to do here is create a connection between 0, 2, 3, and 3. So valid, true, kind, triangle. This is set automatically. Let's see, okay? And you see that everything is working fine. So there is a problem with the multiple mesh faces here, which actually is being set properly because we did it in the managed mesh face collection. But anyway, in this case, I'm using 4 points with 2 different connection schemes in order to create one mesh with 2 triangular faces and 4 vertices. So the connection scheme tells the construct mesh which vertices must be connected to create either triangles or quads. As I told you, in Kangaroo 2, there is one particular way of simulating the origami structures, which is based on this initial scheme that we saw here at the beginning. So origami is basically simulated using the hinge component that requires this kind of mesh scheme, which is basically a mesh with a diagonal line, which would be the folding line, and then 2 opposite vertices, which will be the tips. They will be rotating around the folding line. This scheme is good for a bunch of application, of course, but when you deal with some particular, let's say, origami pattern, then in that case, this kind of workflow can be inappropriate. And limiting, okay? So that's why I want to show you a couple of different ways to create origami structures and origami behavior. The first one is always based on Kangaroo 2, but you will see in a while that there is no origami force or origami goal used in this simulation. So what I want to simulate is this kind of roof that can slide along these 2 round rails and then pack towards this endpoint here. So the simulation will go like this. You see that we have this kind of behavior, and we have an angle that defines the opening when it goes to 0 and close of this system. Okay, so you see that everything works very, very smooth, but yet, as I will show you in a while, there is actually no origami function or origami component in this definition. So I'm going to turn off this simulation. I'm going to turn off the output of this simulation, and I want to start from scratch. So you see, basically, everything is based on the two rails, which are these two arc curves that you see here. One with a radius of 5, one with a radius of 10. So just two simple arcs on the XY plane. Then I took the endpoint of these two curves and decided that I wanted to create a surface initially. So I have the two rails. I just needed a cross section, which is this one. So this is the scheme that I have. And I used a sweep two rails to create this surface. Once I had the surface, I converted this into a mesh with the desired amount of divisions in the longitudinal direction. So you see that this slider here determines how many panels do I have in this direction. Remember that this is absolutely necessary because Kangaroo works with mesh objects. So we cannot work directly with the sweep to rails because it is generating a NURB surface. So once we have this mesh here, we already have the base system. We just need to, well, actually there is this Werbert join meshes and weld that I normally use to double check that our mesh has no, let's say, error inside. So you see that what this thing does is basically join meshes together and eventually weld them. But in this case, I'm not using the weld option. I am joining one single mesh, so this is absolutely useless in this case. It's just a redundant control, okay? So basically, yeah, you see that the mesh that I'm using comes from the join meshes and weld, but I could also use directly the mesh surface output, okay? Then what I did with this mesh was, well, first of all, the standard things. So I want to show the mesh during the simulation. And this is something peculiar. I will give you a description of the reason why I have this deconstruct mesh here later on, once we run the simulation. And I'm using a couple of anchor points for this system because you see that this is our system. I want this set of panels to pack in these directions. So these 2 points here must be anchored to this position. Okay, so what I'm doing here, I'm extracting the corners of my mesh object. This mesh corners, by the way, is a utility which is present here in Kangaroo mesh. You see its mesh corners. And then I am selecting only the first 2 points, which are these two here, and I am converting them into anchor points using the anchor component. Okay. And then I am using always applied to our initial mesh, I am using the naked vertices component. This actually extracts all the vertices of a mesh and divides them in between clothed points and naked points. So naked points are the vertices that lie on the border of the mesh, the outer border, while clothed points are vertices that lie in the inside of the mesh. But this mesh has no internal subdivisions. So basically, clothed points, it's simply outputting a empty point set. Okay, so everything is here in naked points. And you see that these naked points lie partially in the inner edge and the other half lies on the outer edge. So what I did here was dispatch these points. So in order to separate the two sets. And then once I had, we can take a point container just to have a look at what's happening here with this first dispatch. You see that in this case, we get the inner points. And of course, on the other list, we will have the outer points. And then what I did was further dispatch this set of points using the same default pattern, which is true false. So basically what I'm saying here is that I want to send to list A 1 point out of 2. So if I plug the result of the A, you see that I am getting rid of 1 point out of 2. Why? Because basically what I want to create with this definition is that these points are going to be kept along the circular rail, while these other points here will be able to fall down due to gravity. Okay, so this will fall down and the panel will be able to pack like this. Okay, so this is what I'm trying to create in this case. And to do so, I must get rid of 1 point out of 2. And I am considering, therefore, you see, this is the point container. And I am also, in this case, you see that I am getting rid, with this call index, I am getting rid of the last point here. And we will discover why I'm doing this in a moment, okay? So I already have the set of points, 1 out of 2, but I want to avoid considering this point here because this, I need it for a different goal. And so all these points here, I'm going to apply this particular goal, which is a goal that we haven't seen so far. It lies in, it's contained in this toolbar here, where you see the on curve, on mesh, on plane. So it is a constraint basically that forces points to lie, in this case, on a curve. And the curve that I'm using for these points here is the inner rail, so the smaller arc. Okay, so you see that this curve input is connected to this arc here, which is the inner arc. Okay, and eventually I am doing here the same thing with the other set, but of course I'm using the other outer arc. Okay, so 1 point out of 2, but the last one I don't want to use it, and I am keeping all these points over the outer arc in this case. And on the other hand, oh yeah, and by the way, you see that I've applied the other set of points, those points coming from B, so basically the even points along the inner arc and the outer arc. I'm using them, as you can see, applying a load to those points. You see that the load is quite, is using quite a big value for the force. This is because all the system is based on this strength here. So you see that it is 15,000. And this is because when you work with this kind of constraint here, in order to have a perfect coincidence between the point and the curve, you must increase the strength that you are using. So by the way, you see that there is also an expression here. This expression says x by 4, which means that these constraints here are working with a strength of 60,000. So as you can see. And this also means that, remember that the anchor point normally have a strength of 10,000. Also in this case, we have x by 4 because we want this anchor point also to stay in place and don't move during the simulation, okay? So all the constraints are actually receiving a huge amount of strength, okay? On the other hand, I took the same mesh, sent it to another workflow, and in this case, I'm calculating all the edges because I need to convert these edges into rigid bars by using a length line with this slider here, so very resistant, very strong springs, basically. There are also here other another point on curve, but sorry, on another point on curve basically. But in this situation here, what I'm doing is this. You see that I extracted all the endpoints, all the corners of my initial mesh. I used I and +1 as anchor points here at the beginning of this structure, and I am using right now +2 and +3 as these points here. I want these points to be the drivers for the packing of my system, okay? So you see that these 2 points here are being used as, for example, another type of anchor point. And you can see that, for example, here I have the original points. I am rotating these points around the XY plane, which is the center of the arcs, by the way. And I am rotating these 2 points using this slider. So if I turn on the preview of this, you see that this slider, what it does is actually take those points, those 2 points, and slide them along the two rails. And you see that this, the maximum value here is 170 degree. I don't want to pack this structure totally, because remember that it is not safe, because normally you should also consider that all these elements here have some thickness, and we don't want to create an ideal packing. So once we have this variable position for our endpoints, basically what I did was use these 2 points here. I am creating a dispatch in order to have them divided into 2 separate channels, and I'm creating this line. Okay, so what I want is that during the simulation, basically what happens is that I also rotate this line, as you can see, and I want these 2 points, these two rotated points, to lie on the line in between them with an extremely high strength. Okay, also. So I need this because I want this system to drive the deformation of the whole set of panels inside. So I must be sure that this extreme here for our mesh will be basically always, let's say, kept together by very strong conditions, like in this case, this anchor. And so we have this anchor for the driver of the packing, and then we have the elastic force applied to all the meshes of my geometry, of my, sorry, all the edges of my geometry. And then there is this anchor point. So I want these 2 points here to become anchor points during the simulation. This is interesting because you might think that as they are anchor points, they will never move during the simulation. But actually we saw that I am also rotating them dynamically. So what this means is that if I use these original points as anchor point, but I tell Kangaroo that during the simulation, they will tend to these target points, and the target points are the rotated version of the same 2 points, then during the simulation, if I move, change the value of this ladder, these 2 points will move, and these 2 anchor points will take the position defined by the moving anchor points. Okay, so it's like having a target point for each anchor point. And during the simulation, Kangaroo will send these 2 points here in the position of the 2 target points. Okay, this is what makes it possible to create a dynamic simulation in Kangaroo. Okay, so you have to work with target anchor points. And last, there is this spherical light, which is basically the component that avoids that when the panels are all packed together, the endpoints could also collapse and basically become coincident with other vertices. And this is actually avoiding that this can happen. Okay, so this is the system that I've created, and now we can take a look at what happened with this simulation. Let me turn off everything that's on the left here of Kangaroo. Yep, so we only see the simulation running. And oh, by the way, it's convenient to avoid sudden changes in values when you run this kind of simulation. So here it is, the application of the strength of the load, especially in this case, is already making this structure fall. Now, this is something that you might find somehow a mistake, and actually it's not properly correct, because if I release the simulation like this, and I am working with rigid bars, this falling that's happening here means that this bar here, for example, is extending a little. Okay, so as you can see, as this point is not moving, and this point is falling down vertically, it means that between this configuration and this configuration, this edge here is stretching a little. Okay, so you don't want this to happen. And in this case, for example, what I would do is try lowering this value here in order to give a very small value to the load. So in this case, for example, you see that if I reduce this to, for example, 1, what we are doing is avoid an exaggerated deformation for this system. Also, what you can do is eventually, if you see this kind of behavior, you might also want to increase the strength of our elastic edges. So you see that here the elastic edge are 15,000, have a 15,000 strength, but you can, for example, find a multiplication factor. I'm not necessarily using the multiplication by 4 in this case. So what I want to do, I want to find another factor, like between 1 and 10. I don't know. Let's see what happens. And if I plug this to the strength of the length line, and nothing happens, of course, because it's the same value, it's been multiplied by 1. But if I increase this, I should start to notice something. Let me see. It is receiving 105,000, and still I see this kind of deformation, which is quite strong. So maybe I could also increase this a little more. Let's see what happens if I do this. Oh, by the way, you see, I'm also not using the rest length. By default, the component is using the actual rest length. So basically, applying a very light load in this case is already producing this kind of small deformation. But we can consider this as a acceptable deformation. In this case, it's very let's say light deformation. If you want, you can also calculate it before and after the simulation and see if there is some stretching of these lines, as it's evident that there is a little stretching, and see if this little stretching that is occurring is something that you might accept or not. If you don't accept this kind of deformation, you have to tweak the values of the strength of your forces. Okay, so you see that it is not enough to give more strength to the elastic bars, to the rigid bars. Sorry, you should also try to tweak the values, for example, between the load and between other forces that are in affecting the simulation. But anyway, this is the simulation already converged. You see that as I have increased the resistance of the bars, they stretch, but they stretch slowly. Okay, and also the load is less intense in this case. I do prefer to run this simulation with the previous parameters because I need these louvers, these panels, to fall down more in a more evident way. Okay, I don't need any delay. I don't want any delay between the sliding of this end section and the fact that these points are constantly being pulled down by a strong force. Okay. And so in this case, you can see that if I start moving this, the initial controller, you see that everything packs accordingly. And I would not worry about the fact that if these bars fall and stretch initially, they are not being stretched more and more if I keep on deforming the system. So there is no further deformation besides the initial one. Okay, so don't worry about this because the system is already rigid enough. Okay. So you can see that you have this kind of nice effect. Now, what happens after? Now, after this simulation, I'm using a different method for recreating the output mesh. Okay, so in this case, for example, I could also use the output where the mesh is already present, of course, but I wanted to show you another method of working with the output from Kangaroo. So now in this case, where the system is particularly simple, we have a mesh, and the mesh only has vertices in the outer border. Okay, and also all the springs that we are using, the length line, are based exactly on the very edges of the initial mesh. So it means and also the load is being applied to basically vertices of the same mesh. So these points are also endpoints for our edges. So this means that Kangaroo places all its vertices, all its particles along the points that corresponds to the vertices of our initial mesh. So what I did here was explode the mesh, the original mesh, and have access to all its vertices, okay? But also, and most of all, I am having access to the connection scheme for these vertices. So this is telling us that in order to get to the original plane mesh, we need, flat mesh, we need to connect its vertices, which are this one, using this connection scheme. Now, when I have the deformed version of my mesh, the vertices are the same, And the connection scheme is the same. So if I use the mesh vertices, which are these ones, to construct a mesh, I can use the original connection scheme to recreate the right connections and recreate the deformed version of the original mesh. Okay, so this is another technique that you can adopt to recreate your deformed mesh after the simulation, if you don't want to work with entwine and so on. By the way, you see that this definition for goals and feeding the solver with all the goals I have created here is structured in a different way. Instead of using the entwine method, I've used a merge method. This is because this definition was translated from the previous version of Kangaroo, which is Kangaroo 099, that we're going to analyze in a while, to the new version, which is Kangaroo 2. Problem is that Kangaroo 099 doesn't accept data trees, as we will see in a while the new Kangaroo solver, yes, it accepts data trees. So you see that goal objects as tree. And therefore, I just maintain the merge command here, the merge function, without flattening the output, because I can keep all the goals separated into 3 branches. But as you will see later on, this same structure will be used in Kangaroo 099 with the merge component. So we already have our final deformed mesh. And what I did here was use some Weaverbird elaboration like picture frame and mesh window that create this kind of border all around the panels that we are getting from the construct mesh. This is the frame, and this is the inner part of the panel. You can also increase this slider to make this a little more visible. You can see. The bad thing with this is that this is not units, it's percentage. So you don't have a uniform width for the frame of these panels. But anyway, this is something that eventually you can easily correct with a different workflow. So once I have these 2 sets of meshes, I took the frame and gave thickness to the frame. You see that there is Weaverbird also has this mesh thicken component that gives thickness to any mesh, and represented this with 2 different materials, like in this case solid black and semi-transparent blue, which is basically simulating something like glass in this object. And so basically this is the final result that we wanted to achieve. So as you can see, the important thing with this approach, this particular approach, is that I am not using not even one origami component. So you see there is no hinge, no fall through, no hinge corners, not anything. Okay, so basically I am building a origami simulation with standard Kangaroo goals. This is because it's a little bit difficult. Let me point it out by displaying the original mesh. Okay, so we have this mesh object here. So it's quite difficult to work on this object with Kangaroo 2 origami methods, which are based, for example, on the hinge component. So the hinge component is asking for this kind of scheme, but we only have quads here. And actually we don't even need diagonals. We just need these 2 polygons, for example, to fold along this common edge, and these 2 polygons to fold along this common edge, but with opposite angles. So this is what happens in the simulation that I just created. I don't use the hinge component because I don't want to work with diagonals, which would eventually make things a little more complex to organize. And I prefer to work with simple Kangaroo forces that give the same effect in the end. Okay, so this is one approach. Now let's deactivate all of these things, and let's switch to another scenario where finally I'm going to use the old Kangaroo physics. So Kangaroo 099. Kangaroo 099 works a little different from Kangaroo 2. The main difference is the fact that it doesn't accept a data tree for the force objects. You see that it says force object as list. Now this is something that doesn't affect the simulation but it is a little more difficult to, for example, extract the right geometry from the output. Okay, that's the only problem that you might get, because you cannot use the entwine method, for example. And so you see that, for example, I use normally this merge component here, where I plug all the forces and then flatten the output in order to have always one single list. So the force object's input will be happy. Okay, so this is the only difference. And what I'm simulating here is this. Oh, sorry. No, I wanted to start with another thing, which is this one. Yeah, this one, exactly. So what I'm simulating here is a particular geometry. Somebody maybe already knows what type of geometry is this. This is a geodesic dome or an icosphere. It depends on how you want to call it. The property of this, the particular property of this geometry is that, yes, it is a sphere, but it has no poles, basically. So it's not the so-called UV sphere, where you have a North Pole and South Pole, and in that case, the topology converge towards the poles, which creates some topological singularities with correspondence to the pole. In case of a geodesic dome or icosphere, in this, as you might want to call it, you have no topological node or topological singularity, because all this sphere is basically uniform in terms of topology. You see, it's made up of pure triangular faces in this case. What are we doing with this one? Well, actually, we are going to create an origami deformation. And I'm going to show you also that I've used pressure for this simulation in order to explain also, as you were interested in understanding how inflatable structures work, I decided to implement some kind of pressure dynamic inside this object, even if it is not absolutely correct, because inflatable origamis, well, is not exactly correct, as we will see in a while. But anyway, we will have pressure here defined here at the bottom, and we will explain how it works. Kangaroo 099 doesn't need, normally, yes, you might want to work with a grasshopper timer connected to the Kangaroo physics. So when you want the simulation to run, you activate the timer and you set simulation reset to false. Okay, but also there is another way of controlling the Kangaroo physics solver, which is double clicking on its icon. The control appears, so you can simply stop, play, pause, or frame by frame and go to the end your simulation. So if I want the simulation to run, I simply hit play, and you see that this sphere starts to have some origami deformation. Now, the Kangaroo 099 origami is based on a totally different principle with respect to Kangaroo 2. So if you go to Kangaroo 099 toolbar, which is this one, you see that there are some differences, which is basically a different grouping for the goals, which are not goals, are named forces. Then there is the solver part, and then there is some mesh and general utilities, okay? Now, if you go into utility, you will find a particular component, a particular function, which is called origami. Now, this is one single component, and it does all the job. And it's way more complete than the hinge from my point of view. So this is the component. By the way, this is a cluster, and we will analyze it in a while. What it asks for is the original mesh, and it asks for two sets of curves. You see, curve and curve. And then number, number, and number. Now, if we go inside this cluster, which is open, by the way, you see that basically inside of it, you will find a well-known behavior, which is basically this. It takes the mesh, extracts the hinge points, and uses these hinge points as fold lines, fold ends, sorry, and tips as well. Because we have, once again, the hinge component here. But this is from Kangaroo 099. It's not the hinge component from Kangaroo 2. Okay, and all the rest of this cluster here, what it, oh yeah, and by the way, converts the mesh into also an elastic net, and also there is a planarized action that takes the quads and maintain, or the polygons, and maintain them like flat panels. Okay, so it doesn't allow folding or bending of the polygons. Now, all the rest is simply calculating the folding angles and also the strength of the goal of the force. Okay, so I'm shutting down the cluster. I go back to this origami component, and I want to show you what's the importance of this in action here. Okay, so you see that I'm using exactly that component. Now, let's go from the beginning before getting to that point. I have a standard NURBS sphere, and also I am creating a mesh icosahedron, which is basically a platonic solid. This is a Weaverbird component, Control Alt click. So you see that there it is, Weaverbird, define, and here is the icosahedron. Okay, it is a mesh object, by the way. So the output is a mesh with 20 faces. And here it is. You will notice eventually that the vertices of this mesh lie on the sphere. But all the rest, the faces are completely sunk inside the sphere. Okay. Then I take this initial closed mesh and use a subdivision algorithm from Weaverbird, which is called the split triangle subdivision. And this is actually creating a higher resolution for this mesh, always based on triangles. Okay. So you see that this is based on how many iterations you want for your subdivision. If you say I want just one iteration, it means that each edge is divided only by one. So you get the same mesh as a result. If you increase this to 2, each edge is being split into 2 segments, and therefore you can create 4 triangles inside this face. If you increase this to 3, each edge is divided into 3 edges, three segments, sorry, and then you have 2, 4, 6, 8, 9 triangles. Okay, so you see that this is a way of creating a high resolution for the original mesh by keeping its triangular topology. Okay, and then I take this new version, extract all the vertices of the new mesh. So even if we have subdivided the mesh, the split triangle subdivision doesn't perform any smoothing of the mesh. So you see that if we take the original mesh, you see that all the vertices of the new one lie exactly on the faces of the original one. Okay, so what I want to do right now, I want to spherify this this object here in order to have the access to the geodesic dome or the icosphere. Okay, so what I did here was use the closest geometry, which is a component from a plugin. But you can also do the same operation. Actually, this was made in the previous version, so it is not brand new as a definition. Actually, I don't remember why I used this closest geometry when you can also use the surface closest point in order to project all the vertices of this split triangle subdivision onto the original mesh, onto the original surface, spherical surface. Okay, so you see that basically this is the vertex of the inner triangles, and it's being projected on the surface of the sphere, which is this one. So all these points actually lie on the outer sphere, and they remember that Grasshopper doesn't change the order of data inside data structure unless you want it to change it. So in this case, this sequence of points corresponds exactly to the same sequence of vertices that we have from the deconstruct mesh. So I extract the vertices, project them onto the surface of the sphere, and then, see what I did here was use them to reconstruct a new mesh using these new vertices, but the old connection scheme coming from the faces output of the deconstruct mesh. So as a result, I get this spherified version of my previous mesh. And once I have this, I created another subdivision, which is called a loop subdivision, that always operates with triangles. Okay, and this is also applying a smoothing to the object. Okay, so it is not only subdividing the faces into subfaces, it is also smoothing the whole object. So this is the final mesh. This is the mesh that I'm going to use. I am splitting the workflow into two parts. The lower part is, well, let's consider this first. The lower part is actually defining a spherical light, which was present also in Kangaroo 099, based on all the vertices of the new mesh. Okay, so all these vertices cannot get too close to the others. Okay, else they will be basically pushed away from this spherical light force. Okay, and this is the intensity, the strength, the radius, sorry, for this spherical light. Then there is this thing which is very interesting. So I extracted all the edges from this mesh sphere, basically, and I started to work with the spring force. Now, Kangaroo 099 elastic force is created using the springs from line component. Okay. Now this is quite a more complex and complete way of simulating springs than the actual length line in Kangaroo 2, and I'm going to explain you why. You see that I am using all the inner edges, interior edges for the mesh. By the way, this is a closed mesh, so there is no naked edge because the mesh is closed. Okay, so all its edges are interior edges. So E1 is empty. E2 contains all the edges of this geometry. And then I use all the edges, giving them elastic properties by plugging them into the connection input. And then I'm also using the length component in order to calculate the length of each of these edges, in order to tell the spring that their rest length is exactly the actual length of the segments. Now, this is not like in Kangaroo 2 with length line. You have to define rest length. In Kangaroo 2, the length line says if you don't provide any value for the rest length, I will assume that all the segments or the springs are actually in their rest length status. So you must calculate the length and plug it into the rest length. And then there is stiffness, which is actually the strength that we have found in Kangaroo 2. So in this case, for example, you see that stiffness is set to a very high value, which is 1000. So what happens in this case? That we have very rigid springs represented by this line with a rest length that is actual their original length. Okay, so we have already created here rigid bars. Okay, now what are all these parameters here? These parameters allow a better representation of the springs and a better behavior during the simulation. Damping. Damping is a parameter that allows to control this phenomenon here. For example, if you have a weight connected to an elastic rope, for example, and you let the weight fall down, the elastic rope will stretch and reach its maximum length, okay? But it won't stop right there. It will stretch a little more, and then because of its elastic force, it will go back and contract a little, and then extend a little, contract a little, and so on. It starts to oscillate around the equilibrium position. This oscillation will end sooner or later. And this time here that the spring takes when it reaches more or less the equilibrium status, before it stops in that equilibrium status, this time here depends on the damping constant. Okay, so this is the meaning of this value here. So you see, it's very accurate simulation with this spring component. Then there are these upper cutoff, lower cutoff, and plasticity that all the three of them allow a better simulation of the plastic phase of materials. So upper cutoff and lower cutoff means that if the spring reaches a length which is higher than upper cutoff, then it stops working as a spring. And the lower cutoff means that if the spring reaches a length which is lower than this value that we plug here, then it stops working as a spring. And also there is plasticity, which is basically if you want this spring, if you want to consider also the plastic phase of the deformation, then you set this limit, and it means that if the elastic deformation, as you see, goes beyond a certain limit that you define here, then the deformation that occurs will not be elastic. It means that if you reduce, for example, some loads or some, I don't know, other strengths, the system will tend to go back to its original configuration, but there is some deformation that will not be reabsorbed by the system. This is the meaning of plasticity, okay? So you see that it's quite a more complete simulation for the elastic properties of a system, okay? Then there is this thing here that you can see it's parameterized, but it is disconnected. Actually, this is something that you might want to use or not. It's another force that says that all the lines that you plug here and are all the edges of my mesh are being kept with an equal length during the simulation. So this means that our edges will not be able to, let's say, have different lengths. They will all have the same length during the simulation, okay? But you see that this is disconnected because it's something that is not that relevant when we have springs which are very stiff, okay? So it's not that relevant. That's why it is disconnected. And then there is this pressure component. Now, this is important to understand because in case you want to work with pressure, you have to know how pressure works. And what I'm going to do, I'm going to show you this with the original mesh activated. And then there is, oh, let me use a wireframe representation. And then I did this deconstruct mesh. Now, I could also use directly the mesh explode command. And I could eventually do something like this in order to have access to the faces directly, which are triangles, and then deconstruct this mesh to have access to a set of 3 vertices. Because pressure, as you can see, is based on 3 points. So pressure is something that you apply over a surface. While load can be applied to a point, pressure cannot be applied to a point. Pressure acts over the face, on the face of the mesh. Okay. There are 2 main types of pressure forces. One is, of course, pressure, and the other one is the wind. So you will also find between the forces there is wind, and this is also present in Kangaroo 2 as a Gold's mesh wind, as you can see. So pressure and wind are still present in Kangaroo 2, of course. They are basic pressure forces, and they both act and work in the same way. So they act on the polygon and not on the vertices of the mesh. So in order to understand where this pressure is going to act, it needs to know which are the 3 vertices of the polygon. So pressure is always asking for 3 vertices, even if you have a quad mesh. So in case of a quad mesh, what happens is that pressure will automatically do something like this. I'm going to create this little scheme representing a quad mesh. So if you work with pressure, pressure will do something like this. Will triangulate your mesh. It doesn't matter actually in which direction the diagonals are created because it simply works using the corners. And actually, if you split this quad in this way, in the opposite way, you get basically the same result in terms of a pressure application. Okay, so this is what happens, and therefore the pressure is applied on this face, on this one, on this, and this. So, for example, even if you give a very low value to pressure level using this slider here, you have to consider that this value is being multiplied not by the amount of faces, but by the amount of triangular faces. So if you have, for example, a quad surface with 4 quads like this one, this pressure level will be multiplied by 8 and not by 4. So it is a very delicate situation. You don't want to exaggerate with the pressure level because else the object will explode. I will show you this in a while. Okay, so let's leave this scheme here in order for you to remember how this pressure works. And okay, so I need access to the 3 corners of each face. And what I did here, I could have done this like this in order to have access to the 3 vertices, and eventually, after all, use a list item of these vertices in order to obtain the first corner, second corner, and third corner into 3 separate channels, okay? So this is one method. But I wanted to point out a different approach. I will leave it like here. This is a different approach. I am using directly a deconstruct mesh in order to have access to all the vertices. Now, all the vertices means that the vertices are not divided by face. They are just a list of all the vertices in our mesh. So in order to understand which vertices belong to each polygon, I am deconstructing the face. Now you see that I'm using the connection scheme as input. So deconstructing the face gives you access to all the indices of the first vertices, the first corners of each panel. So if you see here, for example, these faces says all faces are triangles. You see that they are all T's, and all the first the first indices are 2, 0, 1, 4, 1, 3, 2, 1, etc. And if you take a look at A, it is exactly 2, 0, 1, 4, 1, 3, 2, 1, etc. Okay? While second index is 44, 42, 43, 47, and here it is 42, 40, 44, 42, 43, 47, and so on. And then there is the third one, okay? Of course, D is basically repeating because there is not enough values, but we don't use D because we need only 3 points. So these are the indices of these vertices that are being used in the connection scheme. So if I take a list item and I extract from the list of vertices only the vertices that correspond to the index of A, then in this case, I get the first corner of each panel, B, the second corners, and C, the third corners. These are the 3 points that I need for the pressure component. And that's pretty it. That's how the pressure works. It is connected to the merge component, but it is set to 0. So I do recommend always set to 0 pressure when you work with it, because it's devastating, the effect that it can have. So once we have this, I will simply turn the preview on, turn off everything we have here in terms of preview, and run this simulation like with play. So this is what happens in this moment. Let's play around with these values a little. So we have, oh yeah, by the way, I still need to explain the origami. Okay, so I left it as last item because it's very important in our case. So you see the origami asks for the original mesh, which is connected via this relay. And then it asks different things. It asks what are the valleys and what are the mountains. So in this case, for example, this should be a valley and this should be a mountain, okay? So this is not working on diagonals, on tips, and so on. It works on folding lines. And folding lines can be of 2 types. The folding line that goes, let's say, up during the simulation are the mountains. And the folding line that goes down, during the simulation are the valleys. So you simply feed these 2 inputs here with the edges that represent the folding lines, which is completely different from what we have done so far. Because we needed to draw a diagonal line inside each quad face in order to use it as a folding line. It was not present in the original origami pattern, okay? So what I did here was create all the mesh edges, use all the inner edges, but in order to divide them between valleys and mountains, I used a generic criteria, which was simply dispatching them with a true-false pattern. So we have here an amount of 480. I get 240 here and 240 here. The thing is that these lines are basically grouped randomly. Okay, so if I take this and get rid of the preview, you see that I have this kind of random set of edges. And if I plug this, I get the opposite set of edges. So these are going to be valleys, and these are going to be mountains. Therefore, the deformation that happens on this sphere is totally random, okay, in our case. But later on, I will show you a definition where this deformation is absolutely under control. And then there is the valley angle and mountain angle. So you can specify different folding angle for valleys and for mountains. And I find this very interesting because this allows a total control over the origami effect. And also, if you take a closer look, valley angle says contains a collection of floating point numbers, not one number. So you can also specify different angles for the folding of the valleys. So it gives you another possibility, which is differentiating the folding angle for each of the valley lines, okay? And as well as for the mountain angles. And then there is folding. This is the strength of the effect of this origami. So you define the angle, which is the potential folding that can occur. And you define, for example, with a strength, if you want this to occur with a very low strength or with a higher strength. This can also be higher than 1, by the way. But in this case, due to the let's say, general forces and strengths that I am using, this is enough to produce some result in our case. So this is how origami work in 099. Let me go back to my preview and let's play this simulation. You see that this is what happens. And we can also do, for example, here, little tweaking. You can tweak, for example, the angle. So you see that this there are some polygons that start to bend or fold in a different way. Of course, this is totally random because I separated the mesh edges randomly, but you can see that this thing is behaving like an origami closed surface that's basically folding around the mountain and valleys. What happens with pressure? This is something that is not properly correct because pressure actually what it's going to do is going to stretch somehow the edges of this mesh because it will act like to inflate this ball here. So if I start to increase the pressure value, you see that this thing starts to inflate. Okay, if I decrease it to 0, the origami takes the total control of the situation. If I increase this, well, let me go away from the sphere. If I increase this more and more and more and more, at certain point, this strength here will become stronger than the elastic force. And when it becomes stronger than the elastic force, the sphere will start to inflate without control, and eventually it will explode. In this case, we have very stiff springs that are capable of basically keeping the elastic body together, okay? But if you don't set the elastic property correctly, even a very small value for pressure can make the object explode. You can also apply negative pressures. So if I change this pressure level to -20 to 20, and I do this, this object starts to shrink and to collapse, okay? But you can also apply a positive value for pressure, so it goes back to its original state. Like, for example, this. Set it back to 0, and you have the origami, only the origami working. Okay, and then you have the strength. So the strength of the folding, you can also increase it, and it will be more, let's say, efficient, the way that this origami contracts or expands. Okay, so this is how the origami component works in Kangaroo 099. It's very interesting because it allows a better representation of the origami, and also because it allows us to work with the schemes, the pattern that we have used in our examples here. So these patterns are based on folding lines. So you see red and blue. They are basically valleys and mountains, okay? Or mountains and valleys, depending on which you want to use for each type of folding lines. So if you have access to this pattern, and you have because they are in this website, you can use them. And I do recommend that you work in that case with the old version of Kangaroo because it is easier to implement that kind of behavior. Yeah. And finally, the last one. The last one is a complex structure, always based on Kangaroo 099. You see, it is this triangular grid initially, and it is being converted into this complex mesh made up of triangles. It's just a basic geometric construction that I did here. I exploded the cells in order to have access to all of its edges, And then there is this uh, point on curve, which is basically the starting point of each edge. I could also use the vertices, but in any way, that's how I did it in Kangaroo 099. So what I'm creating here is the connection line between the center of each cell and the vertices of each cell. Okay, so it's basically three radiuses are being created right here, and then what I wanted to do, I wanted to create, starting from this structure, each of these triangle must be converted into a triangle for a mesh object. Okay, so what I did here was calculate the discontinuity points of these cells, and these are basically a data tree with each branch contains the three vertices of each cell, and I took the points which are the actually they are the center points or bifocals. Yes, I can actually. I don't know why it is not working. I think that yeah, actually it is working. Okay. So I calculated the vertices of each cell, and you see that when you create a triangular grid, the points are not visible, but these points, it's important to understand that they are not at the corner, at the intersection of this line. They are at the center. They are just invisible. So if you take, for example, a point container and plug this here and turn on the preview, you see that these are the center point for each cell. Okay, so I'm taking these center points, grafting them in order to have this data tree structure. You see that here I simplified the data tree in order to have, you see, each branch is being defined just by the varying index. So there is branch 0, 1, 2, 3, up to 169. And then here we have the three vertices. Into one branch, there is one single vertex because I used a list item. And there is the same data tree structure, one single index for each branch. Having this simplification for these data trees makes it possible to use one single container. And when you plug all these cables inside this, as the name of the branches is the same for the four data trees, 4 points will converge inside one single branch, which will maintain the same name of the original branch for the 4 different data trees. So you see that we always have 0, 1, 2, 3, etc., up to 179, but each branch contains 4 points, which is one center point and the 3 vertices of each panel of our grid. And then I took this and split all these points once again into 4 separate channels in order to create this triangle here, and then the other triangle, and the other triangle. Once I have these polylines here, they are closed, I can use them to create these surfaces here. There are many things that you can do in order to create these triangular surfaces, or also quickest ways of creating these triangular surface. Actually, I would do this in one single step, but anyway, once we have this, we use the B-rep join in order to create one single B-rep from all these surfaces, and a mesh B-rep, creating this mesh made up of all these faces, okay? So this is the mesh that we are going to use. And of course, there is, in this case, gravity, which by the way is set to 0, so it won't affect the simulation. There is elastic force, which is springs from mesh. This is the alternative in Kangaroo 099. There is this utility that is called springs from mesh, which is exactly the equivalent of the edge length in Kangaroo 2. Okay, so it converts automatically a mesh into an elastic net. With a rest length factor, I want this mesh to don't contract or expand by default, and it's quite stiff. Okay, so there will be no elastic deformation for this mesh actually. Then there is the origami. Now, in this case, it's not like a random selection of edges. Okay, so if we consider we have this grid here, what I'm using as valleys are exactly the original grid lines. And what I'm using as mountains are the inner edges. Okay, so what is going to happen here is that inside this mesh, this green line is going to raise up, and this red line are going to fall down. Okay, um, so this is let's say a controlled selection of lines. Of course, if as I am deriving this geometry from the original grid, when I exploded the triangles, this is one triangle, but this is another one, and this edge is actually repeating 2 times. So I have twice the amount of inner edges inside this mesh. So that's why I'm using the remove duplicate lines in order to take these 540 lines and eliminate the duplicated one and get only 289. Okay, and also in this case, I'm using this in order to avoid duplicated lines, but this is actually redundant. I noticed this just right now because these are inner lines. Okay, so remember that our triangle is this one, and we have created 3 lines per triangle. So there is no overlapping between these sets of 3 lines. So this is absolutely useless in our case. But anyway, I am removing duplicate lines because I don't want these components to be affected by duplicated valleys and mountains. Okay. Also, there is this component here, which is something that we are using this in Kangaroo 099, but there is also the equivalent in Kangaroo 2. You can find it inside the not co, but yeah, this on mesh. It's the equivalent that you might want to use for your simulation if you want to translate this into Kangaroo 2. It's a nice exercise to translate an old definition to Kangaroo 2 because you get used to the equivalent goals that you have in this case. You see that you have on mesh. In goals mesh, there is actually no pool that you can use like pool to surface that we have in Kangaroo 099. There is also no utility that you can use for this action here. And this pool to surface says, give me a constrained surface. So I'm using this surface that I modeled in Rhino, okay, as the boundary or the constrained surface that I want to use for our mesh, which is this one. So during the simulation, I want this mesh, this green mesh, to adhere to our NURB surface that's used as a constrained surface. Okay, how does it work? It always takes all the vertices of our original mesh and pull them towards our surface. So that's why I told you that the equivalent in Kangaroo 2 is actually the on mesh, which takes a point and projects it onto a target mesh. Okay. In this case, we can use a NURB surface. In Kangaroo 2, you must convert this into a mesh, but actually the component works exactly the same as this. And the pull strength, how strong you want this mesh or these mesh vertices to be pulled onto this NURB surface. And finally, there is this equalize, which is useless, especially in this case, because I don't want to equalize the length of these lines because these lines are smaller than this. So eventually, this is something that is not correct. Okay, so don't even plug it into the merge component here. And so what happens when we run this simulation? What happens is this. Let me take the control. Let me go here where we have the control over the angles. Okay, so I want this angle, valley angle and mountain angle to be 0. Okay, and run the simulation. So the only thing that's affecting our simulation right now is the pull to surface. Okay, but as our simulation is performed on a mesh that is extremely rigid, okay, you see that our elastic force is quite strong, okay, and we want this mesh to don't contract and don't expand. Basically, what we see is that we already have an origami-like behavior because we are using a triangular mesh, and triangle cannot be bent internally. Okay, so as we have rigid edges, and triangular panels, this is already an origami behavior. Okay, what we can do right now is increase the valley angle and mountain angle in order to have this triangle to fold along the crease and valley lines. So if I increase this value here, you will see that the mesh will start to bend more and more around the valleys and mountains. And so eventually I can also increase this value quite much. You will see that this mesh will start to contract and will eventually bend or will fold also in this area, in these areas here where it will not be strictly necessary due to the pull to surface. Okay, so all this thing is actually folding according to the origami pattern that we have decided. So if I increase this more and more, this thing will tend to bend more and more. Try to avoid quick jumps in the variation of the angles, because this will eventually result in a non-linear behavior for your simulation. Okay. Another thing that you can do, for example, once you define the angle, it's you see that we used a range. Previously, we used a range between 0 and 1, but this is basically the strength of this folding action. So you can also increase it and have it running more powerfully. Okay. So if I take this slider and increase it, for example, to 14, I can make this folding action be stronger and stronger and stronger. Okay. So, for example, in this case, I can also reduce the way that this nerve surface pulls the vertices, because remember that as the surface pulls the vertices, this is in contrast with the folding that would come from the origami behavior. Okay, so it's like adding a constraint to our system. So I am flattening quite a bit our object, but you see that it behaves exactly like an origami surface, or an origami system. A very complex origami system, actually, due to this, to the shape of this surface. So you see that now the nerve surface is basically not pulling at all. So we have only folding of the origami using the angle. It would be interesting also to work with by differentiating the angle or the folding direction also. It would be nice to differentiate it in order to create some more complex scenario for this origami. But anyway, this is something that you can play with in your homework. I strongly suggest that you don't leave these topics and this stuff, let's say, aside for a long time, because as you will forget basically everything in very few time. So just keep on practicing with this stuff. Okay, so that's it basically for the origami simulation. Remember just the basic concepts. If you want to work with some complex geometry, I do recommend that you take into account the possibility of using Kangaroo 099, because it makes it possible to work not with a simple hinge, like along the diagonal of a quad face, but also using directly valleys and creases, or valleys and mountains, okay, which is the proper way of creating complex origami. For example, you can start playing around like with importing this other pattern, origami pattern in your Rhino via the Adobe Illustrator conversion, and then import all the blue lines and all the red lines, which are divided already by mountains and valleys, and you can start playing around with Kangaroo 099. If you want to work with Kangaroo 2, I just announce you that you will be struggling very, very much in order to, let's say, associate this kind of scheme to a regular mesh. So it's going to be quite difficult to implement the right strategy to convert this pattern here in an actual mesh. But anyway, this is up to you. You can play around with this and see where the complexity lies. But I do recommend that you do this kind of simulation with Kangaroo 099. The other important thing is that not necessarily you must work with origami components. Okay, so in both cases, be it Kangaroo 2 or Kangaroo 099, I showed you that it's not necessary to work, or it's not mandatory to work with hinges or with origami. You can create a very complex simulation, like for example this folding cover here, using standard grasshopper components and also standard kangaroo components without using any origami object. Okay, so it's up to you. You decide how you want to create the system and how you create the set of forces and goals in case you're working with Kangaroo 2. I also do recommend that you install both Kangaroo 2 and Kangaroo 099, not because you can switch from one to the other, because if you decide to work with Kangaroo 099, it's 100% 099. You cannot use Kangaroo 2 goals in Kangaroo 099 simulation and vice versa. But there are some utilities in Kangaroo 099 that are no longer present in Kangaroo 2. For example, I do recommend that you analyze, for example, the planarity display, which is one interesting utility. And there is also a mesh utility here, which is called quad divide, which is no longer present in Kangaroo 2, which is some kind of subdivision, but it's a simple subdivision algorithm. It's not Cotton-Clark, it's not loop, it's not any of them, which at the same time subdivides the surface and also apply a smoothing effect. While quad divide simply take one quad and split it into several other quads. So these are utilities that you might find useful. There is also some very important thing like the remesh, which is something that we didn't discuss, and it's actually is not important for this kind of application. But if you want to start playing with some growth algorithm, then remeshing is fundamental. Okay, and this is something that if you go into Kangaroo 2 in mesh, you see that it simply disappeared, and also in utility you will not find it. So I do recommend that you keep installed both the version Kangaroo 099 and Kangaroo 2, because there are some things that are extremely important. And the last thing, for example, speaking of which, this component here makes it possible to basically analyze the deformation that you get inside your mesh during the simulation and understand if you can eventually bring your deformed geometry to a production process where you use cheap and fast technology, like, for example, cutting technology. Because this planarity display tells you if the faces of your mesh are more or less planar. Okay, so this is something that you might want to investigate further in order to understand what's the use in terms of production and fabrication for your meshes. I will leave it here because I think it's quite important, and you can experiment with it. So yeah, that's pretty it. I don't know if you have any question or any doubt that you might want to discuss. Let's see. This was a class. Yeah.
I have, of course.
yeah. Wait. Okay, Ariel. Yes. This course will give you a diploma. By the way, it's an official McNeil diploma, as I am a certified McNeil instructor. So I will give you an official diploma. And for this, I have just one question. Please make sure that during the registration process, you gave us your full name, okay? So all your first names and all your family names must be in the registration process. If not, please send us an email with your full name in order to emit the right diploma, okay? And Tiziano, tell me.
So first of all, thanks for the amazing course. It was really, really enjoyable, and
Thank you.
There was a lot of interesting things that we should all learn. there are three questions really quick. The first is, will you be able, when you do the assemble of the video, to recap the first component that it was recorded in the beginning of the square? Do you remember that you were explaining about the arch folding and so on, and the beginning of the square that we didn't record it? Will it be possible to?
I will recap all the first part.
Okay.
Okay. So everything will be on video.
Okay.
And I will do it later in the afternoon. So
Sure.
I think by tomorrow you should have already access to the full recording of the full session.
It was also because it was interesting that you were explaining the difference between Kangaroo 99 and 2. Mm-hmm. And the other question, the first one is really quick. It's like in the beginning when I asked about the mesh division, that you said that there are two different things. When you say there are two different things, it's because you are doing different meshes. Meanwhile, if you are just a mesh and you divide it more regular. And if so, the conversion scheme of a division of a mesh will be also in order, or it's fucked up?
Well, actually, it depends. There are several ways of subdividing a mesh. For example, let's do something like this. I'm going to use a mesh plane in this case. So I already have this square mesh with the 10 by 10 faces. Okay, so mesh with 100 faces like this, and I'm going to subdivide it. Okay, so if I well, let's start from scratch. So I'm going to take a mesh with 1 by 1 mesh polygon. Okay, so it's one single quad mesh, this one. So what I can do, for example, is take a different subdivision algorithm. First, I'm going to take the Kangaroo 099 quad divide. So you will see what this does. So this takes the original mesh and asks into how many parts you want to subdivide each edge. So you see that in this case, we are subdividing 5 times. So you have 5 polygons instead of one single polygon. So you have direct control over the resolution of the mesh via the divisions parameters. So if I set this between 1 and 10, between 1 and 10, then in this case, I can decide how many subdivisions I get from this mesh. In this case, what we can do, for example, we can analyze things a little further because I have this, okay? This is a mesh with more faces. And I'm going to use the mesh explode in this moment because I want to have access directly to the mesh faces, okay? And I will take, for example, the, I don't know, like area component, mesh area component, okay? As the order doesn't change, these points are ordered exactly like the mesh faces, okay? So if I take a point list and apply it to this centroid and take a look at which order is being used, like in this sequence, you see that we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the order is maintained with this kind of subdivision because this is a regular subdivision, okay? So no matter how many subdivisions you create, you always have this column-like sorting of your polygons, of your faces. Now, and this is because of the quad divide, okay? Extremely regular subdivision algorithm, okay? What happens if you use more complex subdivision method? Like, for example, one for all, the Catmull-Clark subdivision, which is one of the more interesting. Now, if I do this, if I apply Catmull-Clark to this mesh, you see that something strange happens. It's true that I am subdividing the original mesh in one polygon becomes 4 polygons, okay, as you can see. But there is also some smoothing occurring right now. Now, this is part of the algorithm. Catmull-Clark subdivision not only converts a low resolution mesh into a high resolution mesh, but also smoothen the mesh up. You can decide to don't smoothen the mesh. So smooth naked edges, you can say, no, I want the corner to be fixed. And this avoid the smoothing of the vertices, okay? But the smoothing, or well, actually the increasing the resolution of this mesh is not controlled the same way as it is controlled with the quad divide. So here we define exactly how many divisions we want along one edge. In this case, we don't. We simply apply the Cutmore-Clark subdivision one time for now. One time means that each quad is divided into 4 quads. But if I apply this 2 times, each of these quads will be divided into 4 quads. So we pass from 1 quad to 4, and then from 4 to 16, and so on. Okay, so if I say level, you must parameterize this level with a slider between 1 and 3, no more than 3. Okay, because as the resolution becomes too high and Grasshopper could crash. Okay, now we are working with a very simple mesh. This is not the case, but in any way, this allows a maximum of 3 iterations. So 2 becomes like this, and 3 becomes like this. Now 3 means that I am getting 2, 4, 6, 8 division for these sides, but I'm not controlling this directly. Okay, so first, this doesn't allow to create a mesh with the desired resolution. It simply increases the resolution according to the amount of subdivisions that you want to make. Okay, and let's see what happens to the order of these faces. So we have 64 faces. We can explode this, and we can take a look at this value here. So you see that things now work differently because we have 0, 1, 2, 3. Why? Because these are the 4 polygons that come from the division of the previous version, which was this quad. So you have 0, 1, 2, 3, 4, 5, 6, 7, and so on. Okay, and you, by the way, you see that 0, 1, 2, 3 is the first, 4, 5, 6, 7 is the second. This is not the third, because this doesn't belong to the same original quad. The same original quad was this one. So the third is 8, 9, 10, 11, 12, 13, 14, 15. And then you pass to the second original quad, which is this one. And you have 16, 17, 18, 19, 20, 21, 22, 23, 24, etc., etc. Okay? So it's a totally chaotic set of polygons. Well, not that chaotic, it is understandable, but it's very difficult to operate on this mesh once you have applied the Cutmore-Clark subdivision. Okay? So yes, subdivision affect the workflow because it can mess things up in a very weird way that makes it very difficult to reconstruct, for example, I don't know, say you want diagonals, for example, in this case, it becomes quite difficult, okay, because polygons are not sorted in a regular way. So for me, it was very easy in the previous example to, for example, dispatch the polygons and understand and how to order them, to sort them by diagonals, okay? In this case, it would be a little more complex.
But if I understand correctly, when you use quad divide, you should still work in the how it's called, the definition of the tree in order to make diagonal. It's not. I mean,
actually, yes, but this is something that you cannot avoid. I mean, for example, in this case, if I work with these faces belonging to this quad mesh here, and I explode it, and I have this order, what I need to do in order to work with diagonals, once I have this grid, I have to build all the diagonals, okay? And not only building the diagonals is not a real problem, because once we have the faces, we can deconstruct mesh these. We have access to the 4 vertices, and we can, for example, dispatch these vertices here. And here we will have vertices 0 and 2, and here we will have vertices 1 and 3. So if I dispatch these once again, I get only the diagonals. If I create a line between these points, like this, I have these diagonals, okay? So diagonals are not the real problem. The real problem is that once I have these diagonals, I have to split this quad into 2 triangles, and I have to tell Kangaroo that this mesh here, made up of 2 triangles, must use this as a fold line, and this vertex as tips. So this is something that makes it mandatory to understand how these faces are sorted inside a data structure. And this makes it mandatory to create some, let's say, specific data tree structure. So in this case, for example, I would take this mesh explode. I understand that these faces are all sorted into column, divided by columns. So once I have the diagonals, I will take eventually these 4 vertices here for each face. I would eventually create a list item, take all these vertices, isolate them into 4 separate channels, and then create a 4-point surface from this thing here. So I have converted all the faces basically into NURB surfaces, which can be used in order to create a surface split, where I split all the surfaces here. Let's flatten them with all these lines. Let's flatten them. If everything is set up properly, I should have 81 surfaces and 81 lines. Okay. And so this command here. Oh, sorry. I think I should. Yeah, I think this is 162. Yeah, no, it's correct. It's correct. These are the fragments. Okay. So I get fragments, which are basically 2 triangles per panel, as you can see. This is not diagonal. Diagonal is thicker in my preview. So these are basically 2 triangles grouped into one single branch. Okay. So if I take a look at this, what I get are 2 trimmed surfaces. Okay. So what I'm going to do right now, I'm going to join these 2 together in order to have one single brep inside every single branch of this data tree. And once I have this, I use the, how is it called, simple mesh, in order to convert this into a simple mesh. So each of these now is a mesh made up of 4 vertices and 2 triangles. Here it is. So if I take a look with a panel, this says mesh, and you see that it says 6 vertices. Okay, now this is something that we didn't discuss, but you see, if we have a mesh with 2 triangles, we should only have 4 vertices. Okay, now this happens because simple mesh is just converting the brep into meshes, okay, using the less amount of polygons possible. This means that this is a triangular mesh and this is a triangular mesh, and they are joined together. They are joined together, but they are not welded together. So welding makes these duplicated vertices here disappear. So you have to take this and also apply a weld mesh in order to have a mesh with 4 vertices and 2 faces. Okay, this is important because if you don't do this, you will get errors during the simulation because you have duplicated vertices here. Okay, and so finally we have our data structure with our meshes sorted correctly and ready to be isolated into 2 separate sets. So for example, here, if I have this grid of polygons, let me move a little. If I have this grid of polygons, what I need to do, let me also grab a pencil. What I need to do is to separate all these meshes that are here, which corresponds to this quad, split it into 2 triangles. I need to divide all these meshes here into 2 separate sets, where I have this one, and also this one, and also this one, and this one, and this one. Okay, all of these must be into one set. Why? Because I want this line here to work as a valley, for example, as well as this one, as well as this one, etc., etc. And I want these other lines here to work as mountains. So in order to do this, as I am working with a regular set of polygons, which are ordered in columns, it's very easy because I need 1 polygon out of 2 in vertical. So the first thing that I do is basically dispatch all these polygons, okay, into 2 sets, and take, for example, these, which are the odd polygons, into a set, and this one, which are the even polygons, into another set, okay? So once I have them, I will use them in order to divide into between increases or mountains and valleys. That's what we did in our definition. So yes, the order is fundamental. If you don't have the polygons in order, it becomes very difficult to organize them into the correct data tree structure in order to work with them with valleys and mountains. That's the real problem.
Amazing. It looks everything so simple when you do it.
Well, it's actually just a little experience. It's not rocket science.